All right, so we're back at it again here, working out of chapter 20. This is the third lecture in our series of work in chapter 20. And I think this one will be the last in terms of just a lecture. And then next Tuesday, what I'm hoping to do is like a problem solving day, okay? So more details on that. There'll be a link for you to join a problem solving session on Tuesday. And then it's time for another exam, all right? So keep that on our radar. Now, 2 lectures ago, we started to learn about this concept of entropy. We gave it the symbol S. We said it's the disorder in a particular substance. The entropy change is the change in this disorder associated with the reaction. Really what we meant by that was that we're looking at the number of different ways or microstates that our chemical system or material can distribute its energy. So we learned how to predict the sign for a chemical or physical process. Hopefully you've gotten good at that. You're going to see that in the online homework for sure. We also learned how to use this summation rule to compute entropy changes for different reactions using our so-called standard molar entropy values, our S0 values. And that standard molar entropy is sort of like the entropy a particular material contains, if you want to think about it that way, under standard set of conditions. And remember, specifying that standard set of conditions is very, very, very important, okay? And I just want to highlight that right here, whenever you see that little 0 behind the variable, that's to specify the standard state conditions, okay? If that 0 is not there, it's non-standard conditions, okay? So it's actually pretty important to look for that 0. Now last time, in the last lecture, we continued upon this idea of entropy. And we defined something called the second law of thermodynamics. It's a really big equation to compute our delta G, our change in Gibbs free energy. And that second law mathematical relationship essentially allows us to compute that delta G. And the importance of that is really, really crucial to understand. Because if delta G is negative number, the reaction is going to occur. It will occur. We say that's spontaneous. And the reaction's only spontaneous as written if delta G is negative. On the other hand, if delta G is positive, the reaction won't occur under the set of conditions defined. If delta G is positive, the reaction's non-spontaneous. So computing delta G is really cool because if we can compute that number, we know whether this reaction is spontaneous or not, whether it will happen or not, under the very specific specified conditions that we're considering, all right? Now in this lecture, what are we going to do? Well, we're going to expand upon the things that we've already talked about, and we're going to add a few more tools to our toolbox to compute delta G. We learned about that one equation last time. Today we're going to learn about a few more options. There are going to be several, and we'll work a few sample problems as we go through today's lecture. One option is we're going to use this rule right here that I'm going to call the summation rule. This summation rule, you've actually seen approaches like this before. Back in General Chemistry 1, you computed the enthalpy change of a reaction. This is a triangle, okay? It's kind of messy, unfortunately. My pen's not the greatest, yeah? But you computed the standard enthalpy change of a reaction back in chapter 6, okay? And you used the summation rule to help us do that. Earlier in this chapter, we even used a summation rule to compute entropy changes, or changes in delta S. So it turns out that this rule is going to be really, really similar to that in terms of how we're going to use it, okay? I think you'll find it pretty straightforward if you understand those other options. Now, that's really good to compute the standard Gibbs free energy change for a reaction at 25 degrees Celsius. But if we're not using that standard temperature, if we're at a different temperature, what can we do? Well, there's other options. One thing is oftentimes we can assume the change in delta H and delta S is negligible. So in other words, what I mean by that is if we vary the temperature, if we move away from standard temperature, if we move away from 25 degrees, if we make the assumption that these numbers don't change very much, we can still estimate delta G. That's another approach. And lastly, the third approach that we're going to consider today's video is to actually sum together or add together individual reactions and their delta G variables or values. In summing together the reactions and the values for delta G, we're actually going to be able to learn how to predict the delta G0 for the summed reaction, okay? And I'll show you what I mean by that once we show an example. It's actually really similar to what you all did back in Gen Chem 1 in Chapter 6 as well. All right, so let's just kind of dive into this discussion then here for today, okay? So way back when, in Chem 1307, you used a summation rule to compute enthalpy of reactions under standard conditions, okay? And to help us do this, where we started with that in Chapter 6 is we wrote formation reactions for various different substances. And you can write a formation reaction for any molecule that you really want to. And the way to do that is you learned about a rule to write these formation reactions. It was one of the learning objectives way back when in 1307, okay? But the rule to write these formation reactions is you always make 1 mole of the compound. It's really, really crucial that you make 1 mole of the compound. And you form that compound from its elements with everything in its standard state at 298 degrees Kelvin. So if I'm going to write this so-called formation reaction for carbon dioxide, what I would write is I'd start on my right side of my arrow by writing 1 mole of CO2 because that's my desired compound that I want the formation reaction. I'd also make sure that I specify its standard state at 298, which for CO2 is of course a gas. Notice I'm making 1 mole of that stuff. It has to be 1 mole because for the formation reaction it specifies that you always made 1 mole. Now, how am I going to prepare that 1 mole of CO2 in the gas phase? Well, I'm going to take its elements to build it. So I take myself a mole of carbon. In its standard state, it's graphitic carbon, which is a solid. And I'm also going to take 1 mole of oxygen molecules. Now, I should have actually specified that these are gas. So I should write a G in here, okay, with parentheses. That's oxygen gas. Also, I'll take 1 mole of graphitic carbon, combine it with my 1 mole of O2, and I can make my 1 mole of CO2. Now, if I do that, the standard enthalpy of formation for CO2, this is my 0 here because it should be a standard molar enthalpy, is negative 393.15 kilojoules per mole. Now, I can look up that number in a table of standard formation enthalpies. And in fact, that table can be found in your book in Appendix B. That's where you'll actually find all of these thermochemistry variables. Okay, so Appendix B will be pretty useful to you when you're working problems. But what we did with these enthalpies of formation is we then used a summation rule that at the time was referred to as Hess's law. This allows us to compute enthalpy changes for reactions from this tabular data. And the reason why Hess's law works is because enthalpy change was a so-called state function. State function. You may remember that terminology. And basically what that means is it doesn't matter how you get from point A to point B. You can go a circuitous path, you can go a direct path. But if a variable is a state function, it doesn't matter how you get from point A to point B, as long as you do go from point A to point B, whatever you're measuring is the same. So I liken it to an altitude difference. So for instance, we can think of the altitude difference between Lubbock and Denver, Colorado. I could fly an airplane from Lubbock to Denver. I could drive from Lubbock to Denver from the same starting point and the same ending point. It doesn't matter how I get from point A to point B. The elevation change between those two locations is consistent, right? It doesn't matter how I get there, okay? Now, the enthalpy values that you computed back in Chapter 6 tell us something about how much chemical potential energy is stored in the bonds of molecules, okay? So these delta HF0, or standard heats of formation, tell us how much chemical potential energy is stored, okay? Now, earlier in this chapter, we learned about entropy. We gave that the symbol S0. Specifically here, standard molar entropy has units of joules per mole per Kelvin. We learned how to use those values in the summation approach to compute an entropy change. So both entropy with the S and enthalpy, we can use this summation approach. So both of these must be state functions, okay? Now because of that, it stands to reason then that delta G 0 might also be a state function for a particular starting point and a particular ending point, if I specify that very, very specifically, okay? So what we're going to do now is we are going to define something called the free energy of formation. It's going to have the symbol delta GF. Notice the little 0 as the superscript. That tells you it's the standard free energy of formation. This is very similar to what we learned about up here back in chapter 6. It's just that in chapter 6 it was enthalpy, and then we talked about entropy here a few lectures ago, but now we're going to talk about Gibbs free energies of formation, okay? So how can I define what this Gibbs free energy of formation actually is, okay? Well, let's define the delta G0F is defined as the change in free energy, Gibbs free energy, when 1 mole of a compound forms from its constituent elements in their standard states at standard temperature. So the definition for this one is almost the same as what we saw up here, right? We write a formation reaction, we make a particular compound, we specify the formation of 1 mole of that compound, and all we're doing is we're tracking the delta G instead of the delta H, say for instance. Still got to work at our standard conditions, right? Now the cool thing about this is that our free energy of formation of their pure elements in their standard states is 0. So for instance, let's take a look at this data table down here at the bottom of the slide, okay, on the bottom right. This is a table reproduced from a textbook of these standard molar free energies of formations, or delta GF values, for a variety of different substances. Let's take a look at the first 4 entries. They're all zeros, aren't they? What are these materials? Well, it's H2, it's O2, N2, and graphitic carbon. Now, graphite is the standard state reference material for carbon, okay? So all of these have 0 delta G0F values in kilojoules per mole here, okay? And that makes sense, because aren't they pure elements in their standard reference states? And by definition, their delta G zeros are all 0, okay? So no big surprise there. But now let's take a look at some of the other substances. Now these other materials are all molecules, I do believe, except for maybe one. Looks like we have this one right here. If you can see that, it's carbon solid. Diamond. Notice that, and that's the important part right there, diamond. That's a different allotrope of carbon compared to graphite. The carbon atoms are arranged differently. Now diamond is not our standard reference material for carbon. Graphite is, okay? So even if elements have different allotropes, only one gets this standard state, this standard reference material, okay? So as a result of that, diamond is not our standard reference state, and because of that, it has a non-zero delta G formation, okay? Now all these other substances in this table are in fact molecules. We got some carbon monoxide, carbon dioxide, got some methane, and on down the list, okay? So notice then that each of these substances have values for delta G, F, standard, associated with all of them. They all have different values because they all have different free energies of formation. So it's a number that tells us a little bit about that material. Now again, all of these values can be found in Appendix B of your textbook. Appendix B. It's important that you realize that because sometimes you need to look up these numbers in a table Okay, oftentimes these values for our delta G's are in the chapter, okay? But if they're not, you can always find them in Appendix B. Same goes for the heats of formation. Same goes for standard molar entropies. They're all in Appendix B for a variety of different substances. So I encourage you to check out that appendix at some point. Now, why is this kind of cool and useful for us, okay? In other words, what is the power of this standard Gibbs free energy of formation business? Well, I mentioned there's going to be this other summation rule. I gave that rule to you on the first slide for this chapter. It's kind of really important. We're going to be using this one a lot for homework problems, and it's almost certainly going to show up in the exam, okay? So what we're going to do with this rule is we are going to use it and employ the summation rule, here shown in this light green color, to compute my standard Gibbs free energy change for more or less whatever reaction I want to. If we can write a balanced chemical reaction, any chemical reaction that we're interested in, and we're able to locate these key and crucial thermodynamic properties such as delta G zero formation for the reactants and the products, we can now predict whether that reaction will be spontaneous or non-spontaneous at 298 using the summation rule. We really should only apply it to the temperature of 298 because remember, these values in the tables are our delta G zero formation, or our Gibbs free energy of formation, the standard Gibbs free energy of formation, which specifies that temperature. But if we can find the values, if we can write the chemical equation, we can predict whether it's spontaneous or not. And that's kind of cool, right? We can predict whether this reaction will occur or whether it will not occur under standard set of conditions. Now, in addition to the temperature being standard, which is really crucial, it's also going to be important to realize that when I compute my delta G zero reaction, I am always specifying standard conditions. And remember, that also means that the partial pressures of any gases has to be a bar. It also means that if you have aqueous ions, their molarities must be 1 mole per liter. All of those things have to be under standard set of conditions. And that's going to be important later in today's lecture, okay? So I want to stress that at this time. So let's take a look at a sample problem based on some of these concepts and see if we can make sense of some of these things, okay? So what we're going to do is we're going to work an example problem here that's shown on the bottom of this slide once I erase a little bit more to clean things up. Move the slide up. What I'd like us to look at is to try to compute delta G zero reaction from standard free energy of formation data. To help us do this, we're going to consider this particular reaction. We're going to take methane. We're going to combine that methane with 8 copies of O2 gas. We're going to make carbon dioxide, 2 copies of water vapor, and 4 copies of ozone. Turns out that this reaction is a possible route to making ozone in the lower atmosphere. So it turns out methane is not terribly reactive, but other hydrocarbons can be much more reactive than methane, and we can make some ozone, which is a ground level air pollutant, which is not so good for us to breathe, okay? But nonetheless, that's the significance of this reaction. We just want to compute the delta G of it, okay, under standard conditions. Now, how in the world are we going to do this? Well, if we weren't given values for our delta G zero formation, we would actually have to go and look them up. So we'd go to Appendix B of our textbook. Here it says 2B, but for your textbook it's just Appendix B, okay? And we'd look up the standard Gibbs free energy of formation for all of the substances which are involved in our reaction, both the reactants and our products. And that's really our first step. We'd make this data table. Fortunately, oftentimes in your homework problems online, you're going to be given this type of table. You'll have access to this data. On an exam, you're always going to have access to this data. Never think that you need to memorize these numbers for delta G zero formation for compounds. Chemists never ever do that, okay? You look them up in a table. So all that information here will be accessible to you on an exam, and I think you'll be able to find it in the homework as well, okay? But let's say that we can find those numbers. What in the world are we going to do with them, okay? Well, the next thing that we're going to do is we're going to use our summation rule that we talked about. Let's take a look at this, because it's actually not that hard to employ it. So we write it out, and notice that's done for us right here. First step in our solution. We write that the standard Gibbs free energy change for our reaction is equal to the sum of the Gibbs free energy change, standard Gibbs free energy change for formation reactions for our products times the stoichiometric coefficient for each product. And we're going to subtract the sum of a similar product for the reactants, okay? Now, in words, it might be a little bit difficult to understand what that equation says, so it might make a lot more sense to kind of jump into the specific details of the mathematics. So let's do that here at the bottom of the slide, okay? It's something that everybody can understand. We just have to see what we're going to do. So let's start by summing up the term for the products. Well, if we look back to the reaction, we have 1, 2, 3 products, don't we? We have 3 products, so we're going to need 3 mathematical terms in our equation, 1 for each product. And this summation notation just tells us to add up the 3, add up all the terms for the products. So we have 1 term for CO2, we're going to have a second term for water, we're going to have a third term for the ozone. So 3 numbers added together, 1 for each product. All right, now how do we generate a term for a particular product? That's our next step, right? Well, let's look what's done down here in these enclosed brackets. The first step is to take this number, negative 394.4 kilojoules. Now we're not multiplying that by anything. Why is that? Well, if I look at my data table, that's the number that's associated with CO2. It's my delta G0 formation for CO2, isn't it? If I look back to my balanced chemical reaction, what's my stoichiometric coefficient for CO2? Isn't it just a 1? So what I'm going to do is I'm going to take that stoichiometric coefficient, which is 1 for CO2, and I'm going to multiply it by that number, 394, negative 394.4. So the 1's not shown, but it's part of the mathematics, okay? That's my term for CO2. Now this second term right here, notice that I'm going to add CO2's contribution to 2 times the negative 228.6 kilojoules. Now where does that come from? Well, notice here, 228.6 is my term for water vapor, H2O gas. In the balanced chemical reaction, I've got 2 copies of H2O gas, don't I? So I take that value of negative 228.6 and I multiply it by 2. And I add that into the mix. And this third value, look, it's 4 times 163.2. Well, that's my value for ozone, isn't it? My stoichiometric coefficient's a 4. So 4 times ozone's value is what I add into the mix. Everybody see that? Pretty straightforward, right? Now, a couple things, words of caution here to think about. One, if you're going into a problem, you need to make sure that the reaction is balanced. Okay, just to make sure that they're not trying to trick you and then give you an unbalanced reaction. So make sure it's balanced. If it's not balanced, then the stoichiometric coefficients are going to be wrong that you use. Okay, so that's crucial. Another thing that I want you to be really aware of is the details here are extremely important, okay? And what do I mean by that? Well, what's the most familiar way that you're familiar with water? You'd probably say liquid, right? But can't we also have water vapor in the gas phase, right? Can't we also have ice? We have different forms of water. When you look up numbers in these data tables, like in Appendix B, there is generally information about the state of matter, like gas, liquid, solid, maybe different allotropes that's also provided. You need to make sure double check that you are using the right form when you grab a number from the data table, okay? Because from experience, it is really, really easy to pick the wrong number in the data table, such as in Appendix B. If you don't pay close attention to the phase of matter, you could easily pick the wrong number, and if you do that, you're going to get the wrong answer, right? So be sure that you're using the right value. You want to make sure that the delta G formation value that you use in your calculation is fully representative of what you are talking about in the problem. Okay, now here it's a gas, water vapor gas, so this is the right number we plug in chug, right? All right, so with that said, we're going to complete this problem. So to this point, we already probably understand how we got that term. We only have to deal with the second term. So we added up the delta G formations times the stoichiometric coefficients for our products. And now the equation tells us to subtract a similar term for the reactants. Products minus reactants. So we have a little bit more math work to do. So what we do is we look at our reactants. We have two, methane and oxygen. Stoichiometric coefficient for methane is an unwritten 1. So we take that 1 and we multiply it by negative 50.5 kilojoules per mole, because that's our value for methane. For oxygen, it's oxygen gas, 8 copies of it, so we do an 8 times a 0. Notice our values there is 0. Now why is that one a big fat 0? Hopefully you understand that it's what? An element in its standard state, isn't it? And remember we said on the previous slide that for all elements in their standard reference state at 298 Kelvin, our standard Gibbs free energy of formation is 0 for all elements in their standard state. So now fortunately in this table we were told that if I wanted to make your life a little bit more difficult, what would I have done? Just not given you any information for oxygen and made you realize that that's the case, right? And sometimes, the problems that you'll see will actually have that built in. And you just have to remember that standard Gibbs free energies of formation for elements in their standard reference form is 0. You like to see that if you have it in a problem, because of course it adds a 0 term, so this just kind of goes away. You don't have to deal with it, right? All right, so after we understand how we set up this problem, all we need to do is solve it. We just solve it. Plug in the numbers in our calculator. Usually when I'm doing this with a calculator, I'd like to do it kind of sequentially. Like I might multiply this out, and then I'll multiply this out. I'll write down the results on my piece of paper, and then I'll add them all up, okay? I like to be kind of intentional about that just to make sure I don't make a calculation mistake. But you're just adding numbers together, and you do products minus reactants. You get negative 198.8 plus a 50.5, because two negatives make a positive. And last but not least, we come up with our answer. This answer is for what? Our delta G 0 reaction. It's my Gibbs free energy change for the proposed reaction under my standard set of conditions. Since the sign is negative, what does that tell us about this reaction? As written, this reaction is spontaneous. Means it will happen. Doesn't mean it's fast. Doesn't mean it's slow. Doesn't really tell us anything about the kinetics. But it does say it's spontaneous. So given enough time, these things will react to form the products. So hopefully that makes sense to you, okay? All right. Now you may remember way back to Chem 1307, this is again chapter 6, we used this so-called Hess's law relationship to our advantage. What we did there is we worked a slightly different set of problems where we add or sum reactions together. And this allowed us to compute enthalpy changes for a given chemical reaction that results. An example problem back then really looked something like this one, okay? You might read, calculate the standard enthalpy of combustion, for the transition of graphitic carbon to diamond. Well, this sounds pretty exciting, right? And you're given a little bit of information. If we look at what we're given, graphitic carbon plus oxygen makes CO2. Oh, there we're burning the graphitic carbon, basically combusting it. And in the second reaction that we're given, we're told that CO2 can degrade into oxygen and diamond. Boy, if you can figure out that reaction, you can make a lot of money for yourselves, and I guess you could also solve the CO2 problem in the atmosphere, right? Now that one, as you might expect, is going to cost you quite a bit of energy. The enthalpy change, or the standard enthalpy change for that reaction is positive 395.4 kilojoules per mole. Okay, so it's really going to cost you quite a bit of energy. But nonetheless, we're given these two reactions. The first one looks like it's exothermic. That second one is endothermic, highly endothermic. And we're basically wanting to take the information that we're given, these two reactions, and figure out something about a third reaction. And the third reaction is this one. Can we convert pencil lead, our graphitic carbon, into diamond? And if so, what's the enthalpy change for this reaction? So the first thing that you all did back in chapter 6 is you identified a balanced chemical reaction that's desired. And in this case, we want to convert the graphitic carbon into diamond. That's our desired reaction. But we don't know what the enthalpy change is for that reaction. And of course, that's really what we want to figure out here. What is my delta H for that reaction? What was my enthalpy change? Now, if you remember what you did, you basically had to line up these first two equations in a certain way, such that when you sum them together or add them together, you generate the desired reaction. So let's take a look at this. We take the first reaction and we study it. It's graphitic carbon reacting with oxygen to make CO2. The second reaction uses CO2 to make diamond and oxygen. Now, if I add those two together, CO2 is a product here, but it's a reactant here, one copy on each side of the arrow. Similarly, in my first reaction, oxygen is a reactant, but then down in my second reaction, it's a product, one copy of each on either side of the arrow. So if I add together reaction 1 and 2, in fact, I get my desired reaction. So guess what we can do? To find the delta H for that reaction, all I need to do is sum my standard molar enthalpy changes for reaction 1 and reaction 2. I just add them together, and that gives me my desired result. So that's what we'll do. Add the negative 393 to the positive 395, and for this desired reaction, it looks like my delta H0 is positive 1.91 kilojoules per mole. Okay, so that's my enthalpy change, my delta H, associated with this reaction. So this may kind of ring a bell. You've seen this before. It actually was back in chapter 6 in General Chemistry 1. Okay, and the reason why this summation approach works is because enthalpy is a state function. Right? Enthalpy is a state function. It doesn't matter how I get from graphitic carbon to diamond. I could go through this path. I could go through an alternate path, right? But because delta H is a state function, doesn't matter which way I go from the starting point to the final point, as long as I get from here to here, my delta H0 is positive 1.91 kilojoules per mole. All right, so you work those types of problems. That's a Hess's law type of problem. So it turns out that now we're going to come back to that. And I want to show you that example because we can actually compute delta G for a reaction by summing reactions as well. And this approach is going to be almost identical to what we just considered, okay? It turns out that our change in Gibbs free energy for a particular reaction is also a state function. Doesn't matter how we get from reactants to products, as long as we do that in very specified set of conditions, delta G is conserved. It's the same, okay? So if a reaction can be expressed as a series of reactions, the sum of the delta G values of the individual reactions is the delta G of the total reaction. So this process is going to work almost identically to what we just saw. Now there are some rules that we want to kind of remind ourselves of. It turns out these rules are also very consistent and similar to the ones that you learned for delta H back in chapter 6, okay? Sometimes you might have to reverse a reaction, and guess what? If you reverse a reaction, the sign of delta G reverses. So if it was positive, you make it negative. If it was negative, you make it positive. You do that when you reverse a reaction, okay? That's the reaction reversal rule. Now what if the amount of materials has to be multiplied by a factor? Well, it turns out that if you do that, the value of delta G is multiplied by that same factor. So these rules are essentially exactly the same as the ones that you used earlier for your calculation with delta H. It's essentially exactly the same rules. It's the same summation principle as we've seen earlier. There's not a whole lot that's different about it, okay? So what I'd like us to do then to try to familiarize ourselves with this concept, why not work a sample problem, okay? I'd like to try to compute delta G0, should be a 0, I got a little cutoff, for a stepwise reaction, and this is essentially going to compute our delta G0 reaction, summing reactions together. Now when you're faced with a problem like this, one of the first things that you need to do is identify the desired reaction, okay? So that desired reaction is right here at the top of our slide. We want to take 3 copies of carbon solid, and actually we should probably specify what type of carbon that is in the parentheses. It's not done here, but we're going to say it's graphitic carbon, okay? We're going to combine that with some hydrogen, and we're going to make C3H8. And if you're familiar with hydrocarbons, you know that this one is propane. It's like what you use in your gas grills. Okay, so that's C3H8. We're making some propane here. Now we don't know what the delta G0 reaction is for this synthesis of propane from elements, but we want to figure it out, don't we? Okay. I should also point out that what we're doing here is this is a formation reaction for propane as well. So we want to figure out what that delta G0 is for this reaction. Now what information are we given to help us? Well, if we look, we're given 3 reactions, and each reaction has an associated delta G0 associated with it. Very different reactions. In this first one, we're combusting our propane, aren't we? In the second one, we're burning some carbon. And in the third one, we're burning some hydrogen. Okay? Now how can we use this information that's given to help us? Well, remember, when we add our reactions together, we need to make sure that reactants are on the right side. Well, reactants are on the left side. The reactants are on the correct side is what I meant to say. And the products of the reaction are on the right. So when I start to think about combining reactions, such as these 3, I need to line up the chemicals where they belong. And the first thing I notice in this first reaction, the combustion of propane, the C3H8 is on the wrong side. In my desired reaction, that's just a product. But in reaction number 1, the C3H8 is a reactant. So right off the bat, I know that I'm going to have to reverse that reaction. I'll put my C3H8 as a product, and if I reverse the reaction, 5 copies of oxygen is also a product. 3 copies of CO2. Are a reactant. Let me write that a little bit better. 3 copies of CO2 are a reactant. And it also looks like, what, 4 copies of H2O come along for the ride as well. I should write that all these are gas phase, okay, but it looks like they're all gases except for the carbon solid here, okay? So just kind of keep that in mind, because you want to make sure that you're crossing out similar things ultimately, okay? So I put the C3H8 on the product side kind of where it belongs, right? Now, I'll start thinking about lining up the remainder of the substances then, where they belong. So in the next reaction, I've got my carbon solid. It looks like that's also a reactant down here. So that's actually on the right side already. Likewise, hydrogen gas is on the correct side. It's on the reactant side as well in my desired reaction. So I don't have to flip it, okay? So that's good news. I only have to flip that first reaction. Now, I'm going to rewrite this to give myself a little bit more room. I didn't give myself enough. Now the thing is, if we flip a reaction, like we just saw here, what happens to the sign on our delta G0? Didn't we say that it also flips? And since it was a negative 2074, now it becomes what? A positive 2074 kilojoules. Because I flip reactants and products. Keep that in mind. That'll be important later, okay? So moving on then, let's see. Well, in my desired reaction, it looks like I've got 1 mole of my propane being produced. And down here in the one that I just talked about and just flipped, I've also got 1 mole of propane. So I'm actually pretty good in terms of the number of moles of C3H8. I think I'll just leave that reactant alone, or that reactant or product alone. But I need to move on to my other materials now. So let's look at equation number 2. In equation number 2, as it's written right now, I'm using 1 mole of carbon solid. But in my desired reaction, it looks like I need 3, don't I? So I need to multiply that 3 moles of carbon solid, or I need to multiply that first reaction by 3. So I'm going to take 3 moles of carbon solid, and I'm going to combine that with 3O2. Multiplying everything by 3 then yields 3 copies of CO2. Now because I multiplied that entire reaction by 3, I also need to multiply my delta G0 by the same factor. I didn't flip the sign, or I didn't flip the reactants and products, so the sign is still negative. But I do need to multiply it by 3. And if I do that on my calculator, I get negative 1183 kilojoules for that reaction. And it's delta G0. Again, because you multiply by 3, you got to also multiply your delta G by that, and same number. Now what about my last reaction? We already noted that the hydrogen H2 is on the correct side. But it looks like in my desired reaction, I want 4 copies. But in reaction 3, I've only got 2. So it seems like I need to multiply that reaction by a common integer 2. And if I do so, I'll get 4H2 multiplying by 2. And I'll get 2 copies of O2. And that's going to yield 4H2O gas. Now I didn't flip that reaction, but I did multiply it by 2, didn't I? So I need to multiply my delta G0 by that same fraction, that same value. And when I do so, I get 914.2 kilojoules negative. So I think now we're ready to add up these reactions. When I do so, if I look at oxygen, I've got 5 copies over here, and I've got 3 and 2. So sure enough, 5 copies are produced on the right, and I use 5. There's no net change with respect to oxygen. It just kind of goes away, doesn't it? Similarly, for carbon dioxide, there's 3 copies here, 3 copies here. Those just go away. They'll cross out, cancel out, if you want to think about it that way. Does anything else cancel out, or are we done? Oh, look, we got water. 4 copies here, 4 here. Use 4, make 4, no net change. And everything else that doesn't cancel out comes down. So my C3H8 comes down, that's my propane. 3 copies of carbon, solid, comes down to the desired reaction, and 4 copies of H2 gas come down. And sure enough, the reaction that I generate is exactly the same as my desired. So I've added 3 reactions together with a little bit of manipulation to come up with my desired chemical reaction. So if I want to compute my delta G0 for this reaction, this approach that we're describing now tells us that if we add together 3 reactions, all you do is you add together the individual delta G's for the reactions that you sum together. So here, all I need to do is add together these 3 values for the individual reactions that's summed together to make my desired reaction. And that's my answer. It's that simple. And this works again because delta G is a state function. Doesn't matter how you get from point A to point B, as long as you get there, you're set. So my answer here, after I add up those numbers, is a negative 23 kilojoules. Notice that it's real important to keep track of the signs. That first one was positive. These other 2 were negative. Don't lose track of your signs. You always got to remember that, okay? But if you can do that, we can certainly work this type of math on our calculator without much trouble. And we're in business, okay? So just to kind of review the things that we've done here so far in class, we decided that delta G is a state function. We've described a summation approach. This summation approach, for the rule of summation, is essentially mathematically right there. It's all things very similar for computing entropy changes and enthalpy changes previously. It's a really, really similar math problem. And then now we said that we can sum reactions together because delta G is a state function. And we just worked a sample problem for that, okay? So next type of problem. Can we compute the standard Gibbs free energy change for a reaction from only the tabular data in the appendix of textbooks? And remember, in your book, it's oops, that's not going to work. In your book, it's appendix B. B as in boy. Check that out sometime, okay? Because that appendice is very useful for all these thermodynamic values, okay? But can we use information in a table such as that to compute delta G0 for any reaction that we're interested in? And it turns out that we can. It might take a little bit more work, but we can do it, okay? So let's think about how in the world we're going to ever accomplish this one, okay? This one will take us a little bit of time to get through it, but nonetheless, we can. It's not really a big deal for us, okay? So one of the possible initial steps in the formation of acid rain is the reaction that's outlined here on this slide. It's the oxidation of sulfur dioxide, okay? And eventually sulfur dioxide gets converted to sulfate, which is SO3, or SO4 2-, excuse me. But an intermediate in that process makes SO3 gas, okay, or sulfur trioxide. And what we want to do is we want to calculate delta G0 reaction at 25 degrees and determine whether this reaction will be spontaneous or non-spontaneous. Now, it turns out that that's all the information that we're given in this problem. None of this is down here at this point, okay? We're just given this information. Can you figure out, without any of this, okay, whether this reaction is spontaneous or not? No, if you're not given that information, you can't, right? But fortunately, we know that appendix B exists, and we're able to look up key thermodynamic values. So one thing we could do is look up our delta G formation for all the reactants and products and use an approach that we just considered, and that would work just fine. But what if we aren't given delta G formation values? Can we use delta HFs and S0 values? Can we use our enthalpies of formations and our standard molar entropy values to help us? And it turns out that we can. Our approach to solving this problem is several-fold, as it turns out. Ultimately, what we're going to get back to is we're going to use our second law of thermodynamics relationship that tells us that our delta G for our reaction is going to be equal to our delta H0 for that reaction minus our T delta S for that reaction. Now you're probably thinking, okay, I remember that equation from last lecture. The second law relationship is very powerful. Remember, if we compute our delta G and it's a negative number, that means that the reaction is spontaneous. And if it's positive, that means it's not spontaneous, right? So I guess you kind of see where we're going with this, and you need to figure out if delta G is negative or if it's positive. And if it's negative, it's spontaneous. If it's positive, it's not, right? But in the meantime, how do we get there? I mean, how do we calculate this delta G? I'm not given any information right now to help me do that. Well, the trick is before we can use this equation to come up with our answer, we need to first figure out what our enthalpy of reaction is. And then we also need to figure out what our entropy change associated with this reaction is. If we could figure out both of those two things, we're in business. I could plug in a 298 for my temperature, and I could easily compute my delta G just by using the equation, the simple equation. So we need to figure out those two numbers first before we can do anything else. And that's sort of the trick to this problem. So it's not really a trick, it's just kind of long-winded and there's a lot of steps involved. But that's our strategy. So if we're going to use this equation, we need to compute our enthalpy of reaction, our enthalpy change associated with the reaction. That's our delta H. And we also need to compute our delta S. So we've got our work cut out for us. We've got quite a bit of work to solve this one. But let's just jump in and go and see what we can do, okay? I think we can make quick work of it. So let's start by doing our delta H, or enthalpy change. Okay? We know that there is a rule to compute standard enthalpy of reaction. And it's a summation rule. Remember, products minus reactants. So in this particular reaction, I've got one copy of SO3. Just one. So if I look at my heat of formation data for my SO3, and I would get that from Appendix B, I see that it's negative 395.7 kilojoules per mole, isn't it? Now I need to multiply that by 1 because of the 1 in the balanced chemical equation. But that's my only product, and now I need to subtract and turn from my reactants, don't I? My first reactant is SO2. Now notice in the reaction I only have one copy of that, so I need to subtract 1 times the enthalpy of formation for SO2, which is negative 296.8. Now I'm running out of room here, but I think I might be okay in this situation. Now you say, well, I have another reactant, don't I? I have oxygen gas, half mole of that. But look at my enthalpy of formation for oxygen gas, O2. It's 0. And by definition, that's the case. You have an element in standard form, standard conditions. Enthalpy of formation of elements are 0. So half times 0 is 0. I don't even have to worry about that, basically, is what I'm saying, okay? So I'm kind of fortunate in this case because I ran out of space, right, on my slide, but I don't even need to worry about the term for oxygen because it's just 0. So if I'm going to compute my delta H then, I have my negative 395.7 times 1, which is negative 395, and then I'm going to add 296.8. Both of those have kilojoule per mole unit, so the units drive. I've got to do that because, again, this was a negative, and two negatives make a positive, right? If you want to think about it that way. So if you do the math, you get negative 98.9 kilojoules. Now, that's not our final answer. It doesn't tell us anything about the spontaneity of the reaction, but it does tell us that our reaction is exothermic because the enthalpy of reaction is negative. It's going to give off heat. It's exothermic. All right, so we're kind of getting to where we like to be. I mean, we got this delta H, but we're not there yet. What's our next step? Well, remember our strategy was to use that second law relationship. To do that, we still need our entropy change. I haven't talked about that at all yet, have we? So we now need to move on and talk about that one. Let's compute our entropy change, our change in S, delta S, for this reaction. Now, do we remember the rule to do that? We actually talked about that 2 lectures ago. It was, again, one of these summation rules, products minus reactants. So we actually do exactly the same mathematical steps, just using our entropy change instead of our delta H like we just did. So we look back at the same reaction. It's SO3 gas as our product, so it's just products minus reactants. The term for SO3 is 256.8 positive. Now that's in joules per mole per Kelvin. That's going to be important later, okay? But I think we're okay for now. That's our products. I've got to subtract a term from my reactants. Now I am going to run out of space, unfortunately. I may need to come down to the next line. Didn't think ahead. Let me see if I can write a little bit smaller. So I start again by doing the 1 times the 256.8. That's the term for my reactant products. Now I'm going to subtract the sum of values for my reactants. So what do we have in this case? We have 1 copy of SO2, and the value for SO2 is 248.2. And again, here we're computing the entropy change. And then in my balanced chemical equation, I have half copy of oxygen gas, and O2 has a 205.2 joule per mole per Kelvin standard molar entropy. Notice that that is not 0 for the element, and that's because the only possible item or material that has a 0 standard molar entropy, as per the third law of thermodynamics, is a perfectly ordered crystal at absolute 0. So we're not going to be able to achieve that here. Oxygen has a much higher entropy or disorder than that, so it has a non-zero number, right? But you can see where we're going with this, right? We just take the stoichiometric coefficients, we multiply it by the S0 numbers for all cases. We do the products minus the reactants, and then we solve for our delta S0, our entropy change that's associated with this reaction. So 1 times 256 positives at 256.8. No big surprise there. And then we're going to have to subtract, let's see, 248.2 plus, let's see, 205.2, oops, 205.2 times 0.5, 102.6. So you see we're just working the math. And it looks like if we work all that out, I'm getting a negative 94 joule per mole per degree Kelvin. And that's our standard entropy change, right? Entropy. That's the one that, we learned about this chapter. Now the fact that that's negative is not good for spontaneity, isn't it? We'd like to increase the entropy to make reactions spontaneous. And even if we were to predict the sign based on what we know back at the original reaction, you can see that we've gone from 1.5 moles of gas on the left to only 1 on the right. So we would actually predict that the entropy would go down and our change would be negative. That's not good for spontaneity, but fortunately, if I look back to the previous slide, we decided that this reaction's exothermic. It has a negative value for our delta H, and that's good for spontaneity, okay? So we have a mixed bag. It's exothermic, but our entropy decreases. Now, how are we going to figure out what our delta G is? Well, as I just mentioned, we've just computed our delta H0 and our delta S0, haven't we? So we can go back to our second law relationship that tells us delta G is equal to delta H, our enthalpy change under standard conditions, minus our T times the change in entropy under our standard conditions. And now, since we know our value of delta S, we just computed it from the tabular data, we can plug in a number there. We know the value for our delta H0, we can plug in a number there, and all we need to do is solve this. Now, the original question asked us about room temperature, or 298 Kelvin. So we're going to plug in that for our T, aren't we? Now, there's one more thing to think about. Let's start solving this, and we'll talk about that. So I'm excited about my solving for my delta G0, so I'm just going to write that down right away. And then I plug in right off the bat. Let's say I'll plug in my delta S, okay? And my 298, because that's Kelvin temperature. That's easy to think about. So I'm going to subtract 298 times my delta S. My delta S was a negative 94. And look at the units attached to that, joules per Kelvin. Okay, so Kelvin temperature times that, the Kelvin goes away, and we're just left with joules, aren't we? Okay. Now here's the thing. Entropy, again, typically has units of joules associated with it. But what are the units associated with our enthalpy? It's kilojoules, or thousands of joules, isn't it? You really got to be aware of that. And this is very, very, very typical. So you don't want to put just negative 98.9 here, because if you do, that's in kilojoules. The units don't jive with joules over here. So you got to convert one of them. Usually what I like to do is convert kilojoules to joules by multiplying by 1,000. So I'm going to write negative 98,900 joules here instead of 98.9 kilojoules. And in doing that, I've converted to a common set of units, and then I can solve for my delta G by punching some numbers on my calculator. And it looks like if I do that, I get a negative 70.9 kilojoules. Now, that's my answer. And of course, the key bit of information here is this negative sign, isn't it? It's a negative 70.9 kilojoules for my delta G0 reaction. So this reaction, as it's written, is certainly spontaneous. It will occur. And we know that because of the sign on delta G. So this reaction is spontaneous because delta G is a negative number. If we did this calculation and delta G was positive, the reaction will be non-spontaneous, okay? Keep that in mind. All right, so let's move on to just a variant or an offshoot of this particular problem. Let's think about this reaction again that we just considered. And we want to ascertain whether or not the reaction is more or less spontaneous if we increase to 125 degrees Celsius. Now we're increasing the temperature. This is a Celsius temperature. We went from 25 up to 125. So that's a pretty substantial increase, right? And it looks like if you do the math on that, that works out to be what? Oops. 398 Kelvin? Not 298, but 398. We increased the temperature by 100 degrees, okay? So how are we going to deal with this? Well, all we got to do is go back to our second law statement for delta G. And plug in the numbers and solve for our delta G and see if it becomes more negative or more positive or what's going on, okay? So when we do this, we're basically going to plug in the values that we already got for our delta H and our delta S. So for delta H, I'm going to plug in my 98,900 again. And that carries units of joules per mole now. And then I'm going to subtract my T delta S using my new temperature, my 398. And I'm going to multiply that by my delta S 0. When I solved for delta S 0, it was negative 94 joule per Kelvin. So then I got to do all the math, right? I got to do all the math. Let's see what I get if I work the math. Seems like my delta G 0 ends up being equal to negative 61.5 times 10 to the third joules, which is the same as 61.5 negative kilojoule. So what has happened? Well, I increased the temperature to 398 from 298. At 298, my delta G was a negative 70.9. But now at this new temperature, a higher temperature, my delta G is still negative. It's still spontaneous, but it's not as negative. It's starting to move, the number's starting to move closer and closer to 0, isn't it? So at this new temperature, the reaction is still spontaneous. It's just a little bit less so spontaneous, right? A little bit less spontaneous than before. Now, what does that mean? Will it still occur? Yes, it does, okay? But you might think of it in your head as just occurring with a little bit less gusto, if you want to think of it that way, okay? Not necessarily kinetically, or in terms of the rate of the reaction, but it's just a little bit closer to being non-spontaneous. And what that also indicates is that if you keep increasing your temperature, to higher and higher temperatures, eventually there will be a point where the reaction's not going to be spontaneous, okay? So something to think about, right? All right, so that's another example problem. All right, so we've worked a lot of problems now, considering computing delta G spontaneity under standard conditions. And now what I'm going to do here at the end of class is talk about non-standard conditions. And I think this is really, really cool and exciting, okay? Because most chemistry actually occurs at non-standard conditions. And I want you to remember that. And to start off this discussion, what I want you to think about is just a thought experiment that's really common in your life. Water evaporating, right? Everybody's spilled some water on the floor, maybe at your house, your workplace. And after a while, that water just evaporates and it kind of goes away, right? Now, here's the thing. If you look up the delta G0 for evaporation of water, that is water liquid evaporating to water gas, you will find that the delta G0 is a positive 8.6 kilojoules per mole. Isn't that amazing? It's a positive number. And we've learned in this chapter that positive delta G's tell us that the evaporation of water should not be spontaneous. It's non-spontaneous because of that positive delta G. So you're probably asking now at this point, what gives? I know that water evaporates if I spill it on the floor, why is it that my delta G is predicting that this is non-spontaneous, okay? There's a little bit of a trick, and it's not even really a trick, but we just need to make sure that we understand what delta G really is and what it means, okay? And that's important. Remember earlier in class, I made this point, and even in previous classes, that little superscript, the 0, is oh so important, right? Because that 0 specifies standard conditions. Standard conditions, right? Oops. What are our standard conditions again? Well, remember, temperature was 298 Kelvin. You say, well, big deal. I can evaporate water at room temperature, right? So that's not going to help us in terms of figuring out what's going on here. But standard conditions mean more than just that of temperature. Remember, it has to do with partial pressures of gases. It has to do with the concentrations of aqueous ions. And what's of interest to us, I think, here is partial pressure of gases. Notice that water vapor in the gas phase is our product of this evaporation, isn't it? So basically what that means is for my delta G0 to adequately represent the situation of water evaporating from my floor, that the water vapor that results has to be at 1 bar partial pressure after evaporation. That's essentially like around an atmosphere of partial pressure of water. So then you have to ask yourself, well, does the water after evaporation have that partial pressure? And the answer is, heck no, it doesn't, okay? It's much, much, much lower. So when you're thinking about water evaporating from a surface, a floor, after a spill, you are most certainly not at standard conditions, are you? So even though my delta G0 says it's non-spontaneous, that's only for a very specific set of conditions, where in this case, the partial pressure of the water vapor is 1 bar, okay? So I'd like you to keep that in mind. Having that 0 behind my delta G, or whatever term we're talking about, really only specifies those one very specific set of standard conditions. What that also states then is that spontaneity is a function of temperature, partial pressures of gases, and concentration of ions. And we really already know this to be true. I mean, we know that the water evaporates. We know that diamond might form from carbon under a certain set of conditions. So what are we missing then? Okay. Well, what we're missing and what we need to complete our discussion then of thermodynamics is a consideration of what to or how to compute delta G reaction for non-standard conditions when we don't have that little 0 there. Now, delta G reaction can be a useful concept even for systems that are running in non-standard conditions. Our concentration of ions are not 1 molar. The partial pressure of gases aren't 1 bar. Maybe we're at a different temperature. And the thing is that this delta G0 is only for those standard conditions. And these two are only equal if and only if all the reactants and products are in their standard reference states. Again, a bar partial pressure of gas, 1 molar concentration of ions. We got to be at a specified temperature. And if the chemistry occurs at any other condition, this is not true anymore, okay? So how can we account for this? What can we do about all these other conditions that we encounter in chemistry, okay? Because it seems to me that most chemistry occurs under non-standard conditions. Well, it turns out that what we can do is to find a few more equations that are extremely useful to us. So one right here and one right here. I think probably the first one's even more interesting, okay? What this first equation tells us is that for non-standard conditions, whenever we deviate from these standard reference states, the delta G for a process or reaction, that's the one that again tells us whether it's spontaneous or not, can be found as being equal to delta G0. This is my standard Gibbs free energy change for that same reaction. But again, notice that it specifies here standard state. So what we do is we compute our delta G under the standard conditions, and then we add to it another term. And that other term is R times T times natural log of Q. Let's take a second to define these variables. R, nothing more than our gas constant with these units. 8.3145 joule per mole per Kelvin. That's our R. Always going to be R. Always use that number for R in this equation. Our T is, as you guessed it, the Kelvin temperature. Kelvin temperature. Our Q is our reaction quotient. Reaction quotient. Remember back when we were talking about equilibrium chemistry, we defined what the reaction quotient was. And for an equilibrium system such as lowercase a, uppercase a, combining with lowercase b, uppercase b, establishing an equilibrium to make lowercase c and then product c. Remember Q was defined exactly the same as the equilibrium constant, wasn't it? It was the concentration of C raised to the power lowercase c divided by concentration of A. These could also be partial pressures too. Times the concentration of B raised to the stoichiometric coefficients. Remember that discussion. So this reaction quotient is coming back into play. So if I can compute my reaction quotient, I plug that in right here. I take the natural log of it, multiply by R times T, add that to my delta G0, and guess what? That gives me my delta G reaction under non-standard conditions. So this equation is super useful because you can predict whether or not a process or reaction will be spontaneous or not under any condition you want to now. It doesn't have to be just the standard set of conditions. It can be any condition. All right, and that's very, very useful, I think. Now there's one more equation on this slide, the second red box down at the bottom, okay? Take a look at that one for a second, and then we'll work a sample problem when we'll be done with this lecture. In this second reaction down at the bottom, because delta G reaction is 0 at equilibrium, there's no net change in concentration of reactants and products. Delta G0 has to be equal to negative RT natural log of K, where K is nothing more than our equilibrium constant for the reaction. So the second equation allows us to relate the equilibrium constant K to the value of delta G0. All right, so let's take an example problem here at the end of our class today. I think this is our last slide, okay? I know it's been a long lecture with a lot of sample problems, but nonetheless, there's a considerable amount of good stuff here, and this gives us a little bit more time to work on problems before the exam during the next class, which I want to focus on because, again, I want everybody to do well. But in this particular problem, we are going to consider this reaction at 298 Kelvin. It's a balanced chemical reaction, it looks like. We got 4 copies of oxygen, 4 copies, yep, 2 and 2 nitrogen. We're good. We are told a standard Gibbs free energy change for this reaction is a negative 71.2 kilojoules. So we know it's spontaneous under our standard set of conditions. But we're not asked that. Instead, we're told to compute delta G under a specific set of conditions, or the partial pressure of NO is 0.1 atmosphere, partial pressure of oxygen is 0.1, and the partial pressure of NO2 is 2. So you have to ask yourself, are these partial pressures standard conditions or not? And they are not standard conditions. They'd all have to be 1, 1, 1 for this to be standard conditions. So it's not. So what we need to do then is figure out how we can compute our delta G reaction. Makes sense? So to help us do this, we need to remember the equation. We need to remember the equation. And the equation for non-standard conditions stipulates that the delta G reaction for non-standard, that's what's on the left of the arrow, right, is equal to the delta G 0 for that reaction. It's the same reaction, but again, the difference is this 0, okay? I cannot stress that enough. The 0 is there on the right side. It is not there. It's missing on the left side. That's because the right side is the standard condition, but the left side is not the standard condition. Right? So understand, before we go any further, what we mean by that. That's extremely, extremely important. Okay? Do not get confused by that. All right, but if we understand that, we can continue writing our equation. And what the equation says is that if we add R times T times the natural log, which is ln, this is not log, it's ln, the natural log. So when you're computing with your calculator, make sure you push the right button. It's the ln button, not log. Don't use log anymore for this equation. It's ln. But if you compute the natural log of Q, multiply it times RT, and if we add that number that you get to delta G0 reaction, we can in fact compute whether or not this reaction is spontaneous as it is written. That's our approach. This is what we need to do. Now fortunately, they were kind of kind to us, weren't they? Because one thing they gave us in this problem was the fact that the delta G was a negative 71.2 kilojoules. So what I can do then is just write that in to my math for this term, my delta G reaction 0. That's my standard Gibbs free energy change associated with this reaction under standard conditions. Notice that I converted it to joules. I did that to make the units jive with this term right here, which I'm going to compute next. Now, if you think back to that previous slide, didn't I tell you that R was always equal to 8.3145? And that has units associated with it. And those units are joules per mole per degree Kelvin. So you got to convert this one to joules to make the units jive. Okay? Keep that in mind. Once you get good at looking for that, I think that you all will get that. Now, I need to take that number for R, and I also need to multiply it by T. T is my Kelvin temperature. Now, fortunately, in this problem, I was told what that is. It's 298 Kelvin. And then I need to multiply that result times the natural log of Q. I'm going to move down to the next line just because I ran out of space, but you guys know this is belonging up here, right? Okay, wonderful. So it looks like this problem is not so bad anymore. I do my negative 71,200. I'm going to add this other number to it. If I multiply on my calculator here real fast, 298 times 8.3145, I get 2477.7. And then I still need to multiply that by my natural log of Q. Now remember what my Q was, is my reaction quotient. Let's focus in on that term right now. So all this other stuff is just coming along for the ride right now. Now Q is my reaction quotient. It's nothing more than products over reactants. It's defined exactly the same as an equilibrium constant. So in this case, my product is 2 copies of NO2. So what I'm going to need to do, since we're talking about partial pressures here, is I need to write the partial pressure of that gas, which is 2 atmospheres, in my equilibrium constant expression. And I'm going to square it by virtue of the 2 right there. In my denominator, I'm going to have 2 terms, one for each reactant. My first reactant is NO. I've got 2 copies of it in my balanced chemical equation, so I'm going to have to square the term with respect to it. And since my initial non-standard condition concentration, or partial pressure of NO is 0.1, I'm going to have to square 0.1 atmospheres. Likewise, my second reactant is 1 copy of O2. And since my partial pressure of that's 0.1 under this non-standard condition, I need to write 0.1 in as my partial pressure for that. That one's just going to be raised to the first power. Now I've got an equation that I can solve. And that's all I need to do to finish off this problem. If we look way down here at the bottom of the slide now, you can see that's what we're doing in this sample problem. We wrote in our delta G0. We have our R and our T. And it looks to me here like if you solve this, you get 4 times 10 to the third. Take the natural log of that, multiply by RT. You get 20.5 times 10 to the third joules. Add that together with our delta G0, and lo and behold, you get a negative 50.7 kilojoules. Negative 50.7 kilojoules. Now what is that equal to? It's equal to delta G reaction. Now do I want to put a 0 there? Yes or no? That's the key question, right? I say no. Putting the 0 there would be wrong. And the reason why is because this problem is not at standard conditions. And the reason why it's not are these initial concentrations of our gases, or these initial partial pressures of our gases. They're not all 111. They're different from that. They're different from standard conditions. So what we have just done is computed the delta G for this reaction under the non-standard conditions. And we found that the sign on delta G was still negative, wasn't it? So would this process be spontaneous? Yes, it would. This process is spontaneous as written. So even though it's under non-standard conditions, it's spontaneous. And the beauty of all this, the beauty of this problem, and this is really cool, I think, is that for any chemical reaction, under any set of conditions, even if they're not standard, we can use this equation to compute whether or not the reaction will be spontaneous or not. So guess what? Back to our original question about conversion of graphite into diamond, or in this case, the evaporation of water. We said it looks like it should be non-spontaneous. Well, it is non-spontaneous if the partial pressure of the water vapor is a bar, or close to an atmosphere. That's a very high partial pressure. That would be like excessive amounts of water in the atmosphere. I mean, it would be so humid it would rain out, and there would be water depositing on things. There's way too much water. But when water evaporates, it's because the partial pressure in the gas phase is not 1 bar or 1 atmosphere. It's much, much, much lower than that. So if you use that equation, this equation on the next slide, to predict what the spontaneity would be even under those conditions of much lower partial pressure, you would find that it would be spontaneous, okay? The evaporation of water would be spontaneous at far lower partial pressures of H2O gas. All right, so that's it for today. I appreciate your patience. I'm going to see you all next Tuesday. Next Tuesday, we're going to have a problem-solving session. Remember, your next exam's on Wednesday night, next Wednesday night. It's going to be over Chapter 19 and Chapter 20 only. So let's get really good at the problems from these chapters. They're very quantitative. You're going to need a calculator. You're able to use some scratch paper for that exam. But I want you to get really good at working these problems so that we can all do excellent.